Today we are talking about optimization, okay? This is like the application part for calculus. You guys are gonna be able to use calculus to find optimum values. So we are taking notes today on optimization. Again, this is the application aspect of calculus or derivatives, because derivatives is one part, integration is another part, okay? So first off, what optimization is, it is the process of finding a maximum or minimum value of a function. That's what optimization is. You're trying to find the optimum value for the optimum profit that a company can make by producing, you know, X number of iPhones, or you're trying to find the optimum area that you can build around your property to make sure you have the most space for a certain amount of fencing, et cetera, et cetera. And this can be done three ways, okay? This can be done, of course, using your calculator. If you're given a function, you can type in the function and determine those maximum values or those minimum values, also known as your optimum values. Depending on the function, if it is a quadratic, of course, you can always work on finding the vertex, okay? Because if you think about it, like if you have a rocket ship that's going to be shooting up, at some point in time it has to come down. So what's the maximum height of that rocket? Well, that forms a quadratic. And so by finding just the vertex, we're able to determine that optimum value, that maximum height of that rocket. And then of course, the one that we're going to be concentrating on today is by using calculus. And that's also, we find maximum or minimum values, aka optimum values, by finding the first derivative and setting it equal to 0. Okay, we've been practicing that with just standard functions. Now we're actually going to apply that with optimization. Okay, so when it does come down to these application problems, the maximum or the minimum value, that optimum value, might not always occur where the first derivative equals 0. You want to make sure you look at the endpoints as well. Because if you think about it, if a company is producing a certain number of products, right? The smallest amount of product they can produce is 0. So that's an endpoint. They won't produce negative products. And so, that would be considered an endpoint. And then let's say they only have enough material to make 300 phones or whatever their product is. Well, then that would be their maximum number of products they can produce. So it's a possibility that the maximum or the minimum might not occur where the first derivative equals 0. As you can see in this particular graph, here is an example where the first derivative equals 0, and same thing here. But the maximum value, the optimum maximum, is not here at this point. It's actually here when x equals b, because it's the highest point on the graph. All right, so you always want to make sure that you check the endpoints as well if you're given any endpoints in these application problems. So when it comes to finding your optimum values, there's a few steps that you probably are going to need to do, or definitely want to consider doing. First thing you want to do is you want to draw a diagram, okay? Because sometimes, just reading the words doesn't actually help you in figuring out exactly what it is that you're trying to solve. Or maybe you can't visualize the actual shape that they're describing. So drawing a diagram can definitely be helpful. After you do that, number 2 is very important. You want to construct a formula with a variable to be optimized. You want to construct a formula with a variable to be optimized. And so what that means is you, depending on the problem, let's say you want to maximize the area of the field that you're trying to enclose, okay? And you want to enclose it in a rectangle. Well, the formula you want to construct is a formula for the area of a rectangle, okay? So you want to, you'll have to know some of your old school area formulas, volume formulas, surface area formulas in order to be able to create that formula. And then of course you want to do it with a variable you're trying to, trying to optimize, whether it's a dimension or it's the actual area. Step 2 is so important because in order to do 3, 4, and 5, you have to have step 2. So once you have that formula, then you're going to find the first derivative and you'll set it equal to 0. Why? Because if I'm trying to find an optimum value, the maximum or the minimum, that is where the first derivative is equal to 0. So once I get my equation, I'll find the first derivative, then I'm going to set it equal to 0. After that, just like how we did before, we want to test to see which point is actually a maximum, which point is actually a minimum. Then, we'll use our sign diagram to determine which is which. And of course, we're doing this based off of the problem, if we're trying to find a maximum or a minimum. And then when we do that, step 5, we're actually going to identify what is the optimal solution. We want to make sure, though, that if there are any restrictions, we're not looking from, negative infinity to positive infinity, or from, we're looking from like 0 to 300. We want to make sure that we check the endpoints as well. Because again, the endpoints could be where the actual maximum is or where the actual minimum is, the highest or the lowest point. And then if necessary, which a lot of times step 6 really isn't necessary, you want to write your solution in a sentence. So some step 6 usually comes, maybe like in a part D or part E, when they ask you to, justify why it is the optimal solution or something like that. But it's going to be very rare that you'll probably have to write a sentence with your solution and explaining why that is the optimum value. Okay? So we're going to go ahead and do a few practice problems. Okay? We're going to go ahead and do a few practice problems today. So here's your first example. I'll give you guys a second to write it down. Again, this is the first of 4 examples that we have today. A farmer wishes to fence off a maximum area possible to make a rectangular field. She has 150 meters of fencing. One side of the land borders a canal. Find the maximum area of the field. So as you can see in the picture that's already drawn for you guys, it provides that visual for you, okay? They wish to fence off a maximum area to make a rectangular field. So the red represents the rectangular field and it borders a canal. So then that basically means is that, am I gonna put any fencing on the canal?
No.
No, you're not going to, okay? I mean, when you think about it, you probably should, so then that way, people won't fall into the river, but people don't put fencing around canals, okay? So the fencing is only gonna go on the red parts of this diagram. So we have our diagram. Now step 2 says we need to construct a formula to, what's the actual word? Yeah, construct a formula with the variable to be optimized. So right here, and it usually says it in the problem, we want to figure out our maximum area. So because we want to figure out our maximum area, that is the formula that we need to create that's going to be optimized. And since this is a rectangle, what's the formula for the area of a rectangle?
Length times width.
Very good. A equals length times width. Now, so to be able to do this, because remember, this is the same formula that we need to take the first derivative of in step 3. Right now, we have 3 different variables, and we can't have that, okay? You never want to have 3 variables when you're trying to, determine maximum area or minimum whatever, okay? So that basically means is that you're gonna have to find a way to rewrite one of these variables in terms of the other. And from what we know, a part of this question is that she has 150 meters of fencing. That is definitely going to come into play in order for us to make sure that we can write our equation in terms of one variable. Because what does fencing mean? What does it mean to put a fence up?
Perimeter.
It represents perimeter. So basically, in your perimeter, you have 150 meters, okay? Now, for this rectangular field that we are trying to basically create, what would be the equation that would represent the perimeter for this?
2L plus 2W.
So 2L plus 2W is the perimeter of a rectangle. But the thing is that, remember, one of our sides borders a canal.
So 2W plus L.
Very good. 2W plus L would equal our perimeter, which is 150. So that means that this is W, and this is L. So if we added up those three sides, that would give us our perimeter. Again, we don't include the side that's bordering along a canal. Okay? Is everyone following me still?
Yes.
Okay. So this other equation, the equation that I've written in the pink, is that equation that we're going to use to solve for one of our variables to plug in to the equation that we're trying to optimize. So what variable do you guys want to solve for in this 2W plus L equals 150 equation?
We can solve for L and then substitute what we get into the area formula.
Exactly. So we want to, well, and to be honest, we can either solve for L or W. L would be a little bit easier because all we have to do is subtract over the 2W. And then we won't have to worry about dividing by anything. So now, by doing this, we're able to come back over and we're able to rewrite our area equation, the same equation that we're trying to optimize in terms of W. So then we're going to replace L with 150 minus 2W. That's going to get multiplied by W. And so if we distribute over that W, that's going to be 150W minus 2W squared. And now we have the equation that we can optimize, that we can take the derivative of, because now it's in terms of one variable. So now we can move on to step 3. Step 3 says to take the first derivative and set it equal to 0. Remember, we do this because we're trying to figure out that value that could potentially be a maximum or a minimum. Okay, so by setting the first derivative, we need to find the first derivative and then set it equal to 0. So what is the derivative of 150W minus 2W squared?
150 minus 4W.
Very good. So then we need to set that equal to 0, and we're going to solve for W. So I'm going to go ahead and add over 4W, just so then that way I don't have to worry about dividing by no negatives. And then divide both sides by 4. And what's 150 divided by 4?
37.5.
37.5. Okay. So 37.5 is where the first derivative equals 0. That means that on a number line, that value is going to either represent my maximum or a minimum. Okay. Now, we just want to check. We want to be sure that that it is. Okay. We want to be sure that it is. So now we have to plug in our test points. Okay. What's a number that's less than 37.5?
37.
37. What's a number that's bigger than 37.5?
38.
38. Okay, so we're going to plug both of those values into the
Derivative.
We're going to plug it into the derivative. So remember, I'm not concerned about the number, I'm concerned about the sign. Because if this is indeed going to produce my maximum area, then it needs to go positive, then negative on each side of the 37.5. So when I plug 37 into 4, 37 times 4 is a 148. And so 150 minus 148 produces a positive number. When I plug in 38 into the derivative, That's going to be 150 minus 152, which produces a negative number. So indeed, 37.5 is the value that produces a maximum. And then what that means is that that 37.5 is the actual length of, is the actual measure of my width that will produce my maximum area. Does everybody understand that?
How do you know that?
Because when we found that that value of 37.5 after setting the first derivative equal to 0, and then using our test points, we were able to see that basically on the graph at 37.5, the graph is increasing and then decreasing, which makes a maximum at that particular value. And that's what we want. If it went minus positive, then that means it was a minimum, and we don't want that value. We want the value that actually produces the maximum area. So it needs to be a maximum at that point. So now that I have the measure of my width, I'm able to answer my question, which says find the maximum area. Remember, we found the equation for area in terms of W, in terms of our width. So then to find our maximum area, we would just plug in the value of W, and then we'll have our answer. So we're gonna do 150 times 37.5 minus 2 times 37.5 squared. We're going to type that in, and we're going to find our maximum area. So go ahead and do that. Tell me what you get. So then our maximum area is going to be say it again.
2,812.5.
Struggling on my numbers today. And then of course we can't forget our units, which is meters squared. And so here's an example of where we can use calculus to find an optimal solution. So what this essentially means for this farmer who's trying to enclose this area using into a rectangular field, her width of her field would have to be 37.5 meters, and then her length would be some other value. But her maximum area that she can produce with 100 meters of fencing is 2,812.5 meters squared. All right, example 2, it's a short one. We have to find the minimum surface area of a cylinder which has a volume of 330 centimeters cubed. Step 1, it says to draw a diagram. I remember a diagram is just there to help you, okay? A cylinder looks like a can of green beans, okay? And what are we trying to optimize here? What are we trying to find?
Surface area.
So that's going to be the formula that we're trying to optimize for a cylinder. Surface area. What is the formula for surface area of a cylinder?
Isn't it like you have to do like the area of the circle plus the rectangle, so like the radius? I don't know.
Well, yeah, the right idea. It is the area of the circle, not just one, but there's two for the top and the bottom. And then that rectangle that basically goes around to create that lateral area.
Is it 2 pi r squared?
That represents
Because of circles.
That represents the two circles, yeah, because pi r squared is the area of the circle, so 2 makes for both of them. How would I represent that lateral surface area? The part that's on the side.
2 pi RH question
Very,
mark.
very good. Okay, because surface area is not a formula that's in your reference booklet, but the curved lateral area of a cylinder is. So that 2 pi RH represents the size of that cylinder. You just have to know that you need to add the area of the circles on top of that. And so now we have surface area. But when you look at that surface area formula, don't you see 3 different variables? You got surface area, radius, and height, which means that you're gonna have to create a whole nother equation so then that way you can solve for one of the variables and plug in. What other information do you know about this particular cylinder?
The volume.
You know the volume. The volume is equal to 330, which means that that is the other equation that you're going to use to solve for one of your variables to plug in. What is the formula for the volume of a cylinder?
2 pi r squared times h. Is that it? Times height?
Close.
Pi r squared times height.
Pi r squared times height. So no 2, just the pi r squared times height. So that is equal to 330. We need to solve this equation for one of our variables so that way we can plug it in to the surface area equation. Which variable do you want to solve for?
Height.
Height. That would be the easier one to solve for. Now let's just say you're like, well, I want to solve for the radius. That's totally fine. Do realize that depending on what variable you solve for, it could be a little bit more work for one than the other, okay? But by solving for height, it's a little bit easier because all you have to do to solve for height is divide by pi r squared. If you solve for r, you have to divide by pi h and then take the square root. And then you got to keep up with a square root. So I'm going to take that value of h, I'm going to plug it in for h into my surface area equation. So I'm going to have surface area of a cylinder is equal to 2 pi r squared plus 2 pi r. And instead of putting in h, I'm going to put in that expression that we solved for h, like so. Now I am multiplying these two together, 2 pi r and then 330 pi r squared. So when I do that, to continue to simplify this, I'm going to multiply 2 and 330. What's 2 times 330?
660.
660. So it's going to be 660 pi r squared. I'm sorry, 660 pi r over pi r squared. How can I continue to simplify that?
Cross out the pi. Or never. Okay.
Cross out the pi, because everything's being multiplied together, so I can cancel out a pi. Can I cancel anything else out?
One of the r's, so it'll leave you with just the r at the bottom.
Very good. I can cancel out one of the r, so I'll leave just an r in the bottom. So my surface area equation, fully simplified, is 2 pi r squared plus 660 over r. Questions for that equation? Because remember, we need this for sure in order for us to do 3, 4, 5, those steps. Okay, so now step 3 says I need to find the derivative of surface area. Go ahead and find the derivative of surface area.
Minus 666 over r squared, or r To the power of -2.
Very good. 4 pi r. You said 4 pi r, right?
Yes.
Then minus 660 over r squared. Very good. Remember, pi is nothing but a number. It's nothing but a constant. So when you apply the rule, the power rule, you're just going to multiply that 2 and that 2 together. And so the pi will stay where it is and it just becomes 4 pi r. And then, of course, for 660 over r, you have to bring the r up by making it negative and then continue to do the power rule. That's how we got a negative 660. And then r squared. To make it positive, you bring it back down to the bottom. So now we have to do step 3, which is find the derivative and set it equal to 0. So this is step 3 right here. When we set this equal to 0 and we go about solving it, I'm going to go ahead and add over the 660 r squared. Again, I don't want to work with any negatives. Then I'm going to multiply both sides by r squared. Why would I multiply both sides by r squared?
To get rid of the denominator?
To get rid of that denominator. Yes, I multiply both sides by r squared to get rid of that denominator. This becomes, I'm going to swing up here, 4 pi r to the third equals 660. Okay? R squared times r gives me r to the third. So that's how I got that. And now I need to solve for my radius. I'm going to solve for my radius. To get it by itself, I'm going to divide both sides by 4 pi. Please be aware that if you type this into your calculator without using that fraction feature, you need to include parentheses around the 4 pi. Otherwise, the calculator is going to read order of operations and you'll end up with the wrong value. Almost certain that it's not going to be a pretty number. Yep, sure isn't. Did you guys get like 52.5211?
Yes, ma'am.
Okay. So then in order for me to find my radius, I'm going to have to do what?
Cube root it.
I'm going to have to do the cube root. Where's the cube root located in our calculator?
Math.
In math, okay? So I go press the math button. I go down to option
4.
Very good. And then I pull the full decimal from the previous line, okay? Remember, no premature rounding, because that's going to throw our answer off. So when I take the cube root of the non-rounded answer from the line before, we end up with what? To 3 significant figures.
3.74.
Very good. So 3.74 centimeters represents the radius that could potentially produce a minimum surface area, okay? Now, of course, we can do our number line and test to make sure that this is indeed a minimum. I'm going to do that very quickly. A lot of times you can, I'll be 100% honest with you. A lot of times you can skip the step of testing to make sure that it is a minimum, but it is a good way to kind of make sure that, you know, your number isn't something that's like super ridiculous, right? You know, something that's not realistic for a cylinder, a can, you know what I mean? And so a lot of times in the IB problems, you know, they'll say find the value of X that will produce a maximum, you know, and you've already found where the first derivative is equal, or what the first derivative is, and so you just have to set it equal to 0. A lot of times you won't have to do this. This step is only necessary if it asks you to justify that it's a minimum, or to show that it's a minimum, or to explain why it's a minimum. That's really the only time you would need to do the number line, okay? Because a lot of times with these word problems, the value you get when you set it equal to 0 is the value that you need to use. Another reason why you want to do the number line, let's say you got 2 solutions when you solved for R. One of them is going to be a minimum, the other one's going to be a maximum. So then you would need to do the number line to figure out which one is the minimum, okay? So again, you pick a few test points, you plug them into the derivative to see if it produces a negative and a positive. This doesn't produce a negative here and a positive here. Again, 3 and 4 would go into the derivative. And yes, 3.74 is the radius that will produce a minimum surface area. So to actually find the minimum surface area, you want to take that R value and you want to plug it in. I'm running out of space here, but you want to take that R value and you want to plug it into the surface area equation that you got in terms of R. So then that way you can answer your question. Normally I wouldn't do the rounded answer. I still wouldn't do the rounded answer. I probably would still do the full answer, to be honest, because it's still sitting in my calculator. And then I would type that whole thing in and find my surface area, then round that. So our surface area for this is going to be 264, what's the units? Centimeters squared. So that will produce our minimum surface area where we have a volume of 330 centimeters cubed. Very good. All right, this one's a pretty loaded, but it breaks it down into pieces just all together in a paragraph format. Give you guys a second to write this one down. An open rectangular box has a length double its width. The total surface area of the box is 150 centimeters squared. The width of the box is X and the height is H. Express the total surface area of the box in terms of X and H. Use this expression to find the volume of the box in terms of X only. Hence, find the greatest possible volume of the box and the width and length and height of the box required to give this volume. So again, it's a little bit long, but it's really kind of broken up into a few different parts. First off, it says to express the surface area of the box in terms of X and H. Let's treat that as part A, okay? So an open rectangular box, here might be a good time to draw a picture, right? So we have a rectangular box. And it's open. What does it mean how is that gonna affect anything? It being open. Why do we need to know that information?
Because we're not gonna like consider the top part of the area.
Exactly. So we're not even gonna consider this a part of the area. It won't affect the volume any, but it's definitely gonna affect the area, okay? And it says its length is double its width. The width of the box is X and the height of the box is H. Well, if the length is double its width and the width is X, how would I represent the length?
L equals 2W.
L equals 2W. And if the width is X, then the length is gonna have to be 2X because it'll be 2W. Then our height would be H. So we have this labeling here. We also have that the total surface area of the box is 150. So surface area is equal to 150. So part A says to express the total surface area of the box in terms of X and H. Now remember, surface area is nothing but the area of all the faces added up together, okay? So in order to create this expression, we have to find all of the areas of the faces, not the top, because remember it's an open box, add them up together and set them equal to 150. So how would I represent the bottom of my box? That area of the bottom of my box.
2x times x.
2x times x. How would I represent the side, like this side right here? How would I represent this side?
X times h.
X times h. And don't I have an identical side right here? That's the same dimensions?
So 2xh.
Very good. And now to represent the front of the box. How would I represent the front of the box?
4xh squared. Because the back too.
So you're right about the back, but I wouldn't have anything squared. Because to represent the front, it would be just our 2x times h. But because there's a back as well, I'm just going to multiply that by 2 because it's the same dimension.
So is it 4xh?
So then it'd just be 4xh. So when I multiply and I can combine some like terms here, this is going to give me 2x squared plus 2xh plus 4xh. So then I can combine, and this will end up being 2x squared plus 4xh equals 150. Does everybody see that?
Is that supposed to be 6?
Would that be 6xh?
Sure would be. Good catch. Good job. Because the 2xh and the 4xh makes 6xh. Good to know y'all paying attention. Wonderful. So that was that sentence. Express the total surface area of the box in terms of x and h. Now the next sentence says, use this expression to find the volume of the box in terms of x only. So let's label that part B. We're going to do that one next. Let me use a different color. Like a red. To find the volume of a box, what do? Like, what would the formula be if I was to find the volume of this box right here?
Length times
The width times length times height.
Yep, length times width times height. But in this case, since I've already labeled my box the way that it is, instead of putting L times W times H, it would be what?
2x times x times h.
Which equals 2x squared h. But it says specifically that I have to write this in terms of x only, which means that I need to use this expression to solve for h, because it has to be in terms of x only. How do I solve this expression for h?
subtract over the 2x squared.
And then?
Divide by the 6x.
So what's 150 divided by 6?
25.
So this becomes 25 over x minus what's 2 over 6?
1/3.
And then x squared over x is?
X.
Very good. So I'm going to plug that in for h over here in my volume formula. So that becomes 2x squared times 25 over x minus 1/3 x. Now we're going to distribute and multiply. 25 times 2 is 50. So it'll be 50x squared over x. How does that simplify? How does that simplify?
50x.
Just a 50x. And then when I multiply 2x squared to a negative 1/3 x squared, that's going to turn into what?
Negative 2 over 3x cubed.
Very good. So then that would be my expression for volume in terms of x only. Now it says, hence, find the greatest possible volume of the box. And then we'll do the width, length, and height in the last part. So, greatest possible volume is another way of saying what?
Maximum.
Maximum. So that means we're going to need to take the something and do something with it.
Set
The derivative?
equal to 0.
I'm going to find the derivative and set it equal to 0. Okay, so I want you guys to do that right now. I want you to find the derivative. I want you to set it equal to 0. And I want you to give me the x value that gives the possible volume of the box. What you guys get for the derivative?
50 minus 2x squared.
Very good. So when you set that equal to 0, in order to try to find what value of x could produce the greatest possible volume, I add over 2x. Again, that's just a preference. I'd rather not have to deal with any negatives. Divide both sides by 2. That gives me 25. Then I have to take the square root. What does x equal when I take the square root?
5.
5.
Yes,
Negative
ma'am.
Positive 5.
Yes, that also.
Plus and minus 5, okay? Don't forget, when you're solving quadratic equations and you have to take the square root, remember it always produces a positive and a negative value. But remember, we are talking about x, which represents the width of a box. Can a width be negative?
No.
No, it cannot. So our answer here that we want to definitely make sure we use is 5. Now, granted, if we did put -5 and +5 on a number line, because let's just say this wasn't an application problem. This was just a normal cubic equation that we were trying to find the derivative of and determine maximums and minimums. When we plug in test points into the derivative, we would see that when we plug in a -6, that would produce a negative value. When we plug in 0, that would produce a positive value. When we plug in 6, that produces a negative value. So realize that -5, it actually does produce an extrema, but it's the minimum value. We were looking for the greatest possible value. That's why 5 is the maximum, but also again, x represented a width, and width cannot be negative. So we'll actually end up doing pretty much the rest of this all together, finding the width, length, and height, along with the greatest possible volume for this box. Because right here, we already know that the width is 5 centimeters, because that's what x represented, and we solved for x. If the width is 5 centimeters, that means that the length is how much?
10 centimeters.
because it's doubled. Very good. Then the height is found by plugging x into the equation that we found for height back over here. Y'all see that? So when I go to plug in 5, that becomes 25 over 5 minus 1/3 times 5. Can somebody give me that value? That would be 10 over 3 centimeters. So then the volume of my box, I can easily just do length times width times height since I have all the dimensions, or I could plug 5 back into the volume formula that we created over here in part B to get my volume. So let's do that. Let's find out our maximum volume. Anybody got it?
500 over 3.
500 over 3. Of course, you can round up to 3 significant figures. That'd be 167 centimeters cubed, but it is exact. And we also don't have to worry about that whole rounding, potential rounding issue. But there you go. That is how you can use optimization to determine maximum and minimum optimal solutions. That's how you can apply calculus into these different types of problems to determine lengths, measures, areas, volumes, things like that, okay? And it's not just limited to, these geometrical shapes. They can go into equations that model rockets, like I mentioned earlier. It can go into profits and cost and other things like that. So it's not just used for these geometric type of problems. They can be applied other places. I just use these because a lot of times you have to create your own equation for these. And so I'd rather do those together versus the ones where the equation's already given to you. Does that make sense?